We're looking at rates and concentration, and we know that we have these graphs. The first graph is going to be a concentration versus time graph, and the second graph that we'll be looking at is reaction rate versus time. Now, the chemical formula that we are going to focus on will be 2NO plus O2 forms 2NO2, and it's exothermic. And we are going to look at a couple of changes that occur here when we do this work. So first off, when we get started, the forward reaction is happening. We see that there is a decrease in the concentration of our two reactants and an increase in the concentration of our products. Very important here to notice that we have three lines because we have two reactants and one product. Our product concentration starts off as 0, therefore our graph will start off at 0 for the product. Then we also see reaction rate. I'm using red for the forward reaction and blue for the reverse reaction. And we see that they will start to happen and then it reaches a point of equilibrium. Now if we look at an increase in pressure, when we have an increase in pressure, something will happen here to our graph. So if there is an increase in pressure, remember that there's a formula C equals N over V. C stands for concentration and it's measured in mole per cubic decimeters. So when the volume increases, we know that the pressure will decrease. And we know that when the volume decreases, the pressure will increase. So this is very important to remember because when the pressure increases, our concentrations will increase. And this applies to all three of our gases. So what we'll see happen is that all three gases will increase. Now the system, according to Chatellier's principle, will try to establish equilibrium again by causing a decrease in the pressure. So when this happens, a decrease in pressure, we have to go and look at how many moles we have on both sides of our equilibrium. On the left-hand side, we have 3 moles, 2NO and 1O2, that's 3 moles. On the right-hand side, we have 2 moles. So remember, this reaction runs in both directions, and as you can see, to decrease the pressure, the forward reaction is going to be favored. When the forward reaction is favored on our graph, we see that our NO and our O2 will show a gradual decrease. And of course, our NO2, our product, will show a gradual increase. So just remember that that's what we have on our y-axis here. If we now go and have a look at our rate of reaction, remember that for both, the concentration increased, which means that the reaction rate will increase. Rate is influenced by concentration, so we see that the reaction rate increases. But, very important here, the forward reaction will increase more than the reverse reaction, and the reason for that is because the forward reaction is going to be favored. And so we see the forward reaction is favored, it gradually decreases, and we see our reverse reaction gradually increases. Then when we move on, if we have our second scenario, a decrease in pressure, the system will react by trying to increase the pressure, which means that our reverse reaction will be favored. When our reverse reaction is favored, it's important to know what happens. When our pressure decreases, concentration decreases. So our first thing, before there's any rectifying of a balance, is we see that all of the concentrations of the gases will show a sharp decrease. Then the fixing comes. The reverse reaction is the one that's favored. So we'll see a gradual decrease in the NO2 and a gradual increase in NO and O2. If we go and have a look at our reaction rate graph, we know that because the pressure decreases, both the forward and the reverse reaction will show a sharp decline in reaction rate. But then remember that one of them will show more of a decline than the other one. The reaction that will be favored here is the reverse reaction, so we see that there's a gradual decrease, and that means that our forward reaction is going to be lower down on the graph. How do we know this is true? Remember, according to Chatellier's principle, the reverse reaction is favored. Therefore, the reverse reaction is going to experience a smaller decrease in the rate. Then if we move on to an increase in O2, remember an increase in O2 will only increase the concentration of O2, not NO and NO2. The system will counter this by causing a decrease in O2, which means that the reaction that will be favored here will be the forward reaction. And we see a gradual decrease in O2, which means a gradual decrease in NO, and therefore a gradual increase in NO2. We go and we have a look at our reaction rate for the third one. If there's an increase in O2, we see that there will be a sharp increase in our forward reaction, which will then have to decrease gradually, because the forward reaction is the one that is favored. So important here to remember that the increase in concentration of the reactant leads to an increase in the rate of the forward reaction. Then if we move on to the next one, removal of NO, that's removal of nitrous monoxide, which is one of our reactants. We see the system will counter this by causing an increase in NO, and we know that this will lead to the reverse reaction being favored. If our reverse reaction is favored, remember that we will see that NO is going to show a very sharp decline, like that. And if we look at O2, it doesn't show a sharp decline. NO2 also doesn't show a sharp decline. So remember, we want to increase the concentration of the NO, and therefore what we see is that there's a gradual increase because the reverse reaction is favored. Also, there will be a gradual increase in our O2, and therefore a gradual decrease in our NO2. If we have a look at our reaction rate graph for the fourth one, the removal of NO, if we remove the NO, there will be a sharp decrease in the forward reaction because we're removing one of the reactants. So the system will counter that by favoring the reverse reaction, and we see that the reverse reaction that is favored has this blue line over here that shows a decrease. So when we have an increase in temperature, the system will react by causing a decrease in the temperature. The reverse reaction is favored because the reverse reaction is endothermic. So when we have a look at what happens to our concentration versus time graph, we know because the reverse reaction is favored, the NO2 will gradually decrease and the O2 and NO will gradually increase. Now, with our reaction rate, very important, both of these lines, the forward and the reverse reaction, will experience the increase in temperature. But remember that the reaction that is going to be favored here, which is our forward, the reaction that will be favored here, which is our reverse reaction, will show a much steeper increase than our forward reaction. And basically I can just summarize this by telling you that the reverse reaction is favored and it experiences a greater increase in rate. And that's why it's higher up. So because it's favored, we see the shape of the graph there and the red line meeting it. The last one, if we have a decrease in temperature, the system will counter this by causing an increase in temperature, which means that our forward reaction will be favored. We see that both our reactants will gradually decrease and our product gradually increase. If we look at our reaction rate, both of them will experience a decrease in temperature, but now our reverse reaction, who will experience a higher rate change, will have a lower low here. So what we see is that the rate of the forward reaction will have a smaller decrease than the rate of the reverse reaction. And then this will be the shape of our graph. At this point, just want to show you also, what about if we added a catalyst? How would that affect our reaction rate graph? So both the blue line and the red line would increase, and then both would just be at equilibrium again. There is no new equilibrium that needs to be reached. Also important to remember that the only thing that affects Kc value will be temperature.